Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, length of longest valid substring. The problem is very interesting, and in this video, we'll be discussing one harder follow-up of this problem as well, wherein words.length is less than or equals to 10 to the power 6, right? So if you have solved this problem during the contest or after the contest, I would strongly encourage you to try to think of what will be the solution if words.length is less than or equal to 10 to the power 6. In case you are just interested in the follow-up, all the timestamps are there in the description below. Feel free to move back and forth and watch the section you like. So with that, let's get started. The problem says that you are given a string word and array of string forbidden. A string is called valid if none of its substrings are present in forbidden. You need to return the length of longest valid substring of the given string word. So let's take an example. Let's say word is CB4A BC and forbidden contains two string AAA and CB. So basically we are saying that we need to find out the longest substring of this word which doesn't contain any of the forbidden strings. So for example, if let's say you consider this string B AAA, this string is not a valid string. Why? Because it contains AAA and AAA is present in the forbidden list. So we have to figure out the length of the longest substring which doesn't contain any of the forbidden string. So you can see AABC is one substring which doesn't contain any of the forbidden strings, and you will not be able to figure out any string of length 5 which doesn't contain any of the forbidden string, and hence the answer here is 4. So hope the problem statement is clear. Now how to solve this? So as always, if you haven't solved the problem in the brute force solution yet, I would strongly encourage you to pause and try to at least think of the brute force solution by yourself. The brute force solution would be very straightforward. You can just simulate whatever is given in the problem. So what is the brute force solution? You will say you need to find out the longest substring. So this is the forbidden list which contain 3 string AAA, BC and CB, and this is the given string word. You need to find out the longest substring of this word which doesn't contain any of the forbidden strings. Now longest substring, you can say, okay, I will try out every substring starting from every L, and for each L I will say what is the longest substring starting from L, and I will do it for every possible L and take the maximum, and that will be my answer. So that is correct. Let's look at an action. Let's say you have to start with this L. You need to figure out what is the largest R up till which L to R will be a valid string, right? So what you can say that if L to R is invalid, L to R plus 1 will also be invalid, L to R plus 2 will also be invalid, and so on and so forth. So basically what you are saying is L to R is invalid. It means it contains something which is present in the forbidden list as well. So if you consider L to R plus 1, this will also contain the same substring which is present in the forbidden list. So if L to R is invalid, anything that contains this L to R will also be invalid. So L to R plus 1, L to R plus 2, or L minus 1 to R, everything is invalid. So what we will do, the strategy would be to figure out the first L which is, or the last L which is valid. So you will say, okay, I will try with this R. If it is valid, I will try with this R. If it is valid, I will try with this R, and so on and so forth, right? The first place where it become invalid, I will stop there, and the difference between them will give us the largest length of substring if we start from this particular L. We will do it for every L and get the answer. Now if we somehow need to figure out whether some L to R is valid or not, so we need to figure out whether this L to R is valid or not. So one way could be to just apply the definition of valid substring. The valid substring would be valid if none of its substring contain the forbidden string. So you can say, okay, I will iterate over all the substrings of this L to R. So I will iterate over A, 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 C, A, C, B, and so on, so forth. I will iterate over all the substring. If any of them is present in the forbidden list, I will say that L2R is not valid. Otherwise, L2R will be valid. But the overall complexity will boost up for because of that. So you are trying out every substring already. Now, on top of it, for determining whether it is valid or not, you are saying that I will try out every substring of this substring again, right? And then I will check some whether it is present in this list or not. So some other factor as well. So this will be too much. Let's try to optimize it. So a very simple optimization could be based on the fact that L2R minus 1 is already valid. So if if L2R minus 1 is not valid, you will not try L2R, right? You will stop there. So if L2R minus 1 is already valid, then figuring out whether L2R is valid or not is easy. So we are saying that L2R minus 1 is valid. So what are the new strings that got introduced because of R? New substring that got introduced is B, BC, CB, ACB, or AACB, right? So these are the new substrings that got introduced because of this newly added character R. So if we can just check these 4 substrings and see if they are not present in the forbidden list, then we can say L2R is valid. Why? Because L2R minus 1, anything in this range L2R minus 1 is something we have already checked. Because this is already valid, we already know all the substrings that are present in this particular range will be valid. So we'll just check the ones which got newly introduced, and that will reduce 1n from the time complexity easily, right? So the pseudocode for the current algorithm would look something like this. What we are doing, we are simply iterating over all the L's as we have discussed. For each L, we will try to find the maximum R possible. Now, once we find the maximum R possible, we will simply update our result to max of result comma R minus L. Now, what is the maximum R possible? Maximum R possible can be figured out by simply iterating over R one by one. So we'll start R from L and we'll keep on incrementing it if it is valid. If it is not valid, we will simply break out, right? Now, how to figure out whether it is valid or not? Again, we will look at all the newly introduced substrings. Now, what are the newly introduced substrings? All the substrings that ends at R and starts at anywhere between L and R. So we are checking every substring that starts at anywhere between L and R and that ends at R. So for each of these substring, we'll check if it exists in the given forbidden list or not. If it exists, we'll simply break out by setting is valid to false, right? What is the time complexity of the entire solution? This loop will run order n time. This loop will also run for order n time, right? This loop can be optimized to the length of the largest string in the forbidden string, right? So if forbidden string contains a length of 3, there is no point checking whether a string length of 4 is present in the forbidden string or not, right? So instead of iterating over everything between L and R, we'll simply iterate over those which basically R minus length of forbidden string, right? And similarly, this part, figuring out the substring itself, will also be the length of forbidden string. So the overall time complexity would be n square multiplied by length of forbidden string square multiplied by log n or log of f, which is the number of forbidden string. So this log f is not actually log f because we are comparing 2 strings here. So comparison of 2 strings requires order n time if the length of the string is n. So this log f is not actually log f. There will be some constant factor as well, in particular fl itself. But let's now forget about this fl. This is the overall time complexity for now. This n square because of this 2 loop, and then fl because of these 2 things, right? Now this will surely not pass because n itself is 10 to the power 5 and fl is 10. So this will not pass. Now we need to optimize this. Look at this loop, the innermost loop. What it is doing? It is simply iterating over all the newly introduced substrings and figuring out whether any of them is present in the forbidden list or not. So if let's say for this R you already know that if for this R you already know that this L is present, you can simply, instead of iterating, you can simply say, okay, I know there is something which is present, so I will simply skip, right? So the idea is, can we somehow match what all strings are already present in the given forbidden list. So basically we are saying that we will maintain an array something like this. How to maintain this array is a different question, but basically if we have something like this, we will be able to optimize it. What this array is, basically it says that if you start from this particular index I, everything up till 9 will not match. In other words, A, AA, AAC, AACB, or everything up till this 9th index will not match. Similarly, it says that if you start at this index, everything up till index 2 will not match. Starting from index 3, it will match, right? So basically it says that everything up till 2 will not match if you start from here, but if you take anything after that, it will match. So surely CB is present in the given array, given forbidden array. So once we prepare this list, answering this kind of query is very easy, right? So let's look at how it actually help in reducing the time complexity. So if you look at it, we have this forbidden list, right? Now we want to find out what is the maximum R possible for this particular L, right? So we said that, okay, this 9 denotes that everything up till 9 will not match if we start from here. So it means A, C, anything up till this will not match. So for this L, this R up till this R is valid, assuming that we have only considered substrings that are starting from this L. But as per the definition of valid substrings, you have to consider all the substrings. So you have to consider the substring that is starting from this as well, right? Similarly, you have to consider the substring that is starting from here as well, right? Because you can see, if you just declare a substring valid as per starting from here, it is not always true, because you can see in this example itself there exists a substring which starts from somewhere inner position and it's present in the forbidden list as well. So for every substring starting from 0 is something we have taken care of, and we have said that everything up till this particular R is valid. Now let's take care of all the substrings that are starting from this particular index, right? So for this particular index, again the value is 9. It means that it says everything up till 9 is valid. So A, AC, ACB, ACBA, everything is valid. So for this L as well, everything up till this R is valid. So basically the statement that for this L, everything up till 9 is valid is still true. Now let's talk about this particular, or all the substrings that are starting from this particular index. Now it says that everything up till 2 is valid. It means you can't take anything after 2, right? So if you take anything after 2, it will become invalid, because you can see CB is present in the given list as well. So in this case, it's saying that you can't go above 2. So your R can be maximum 2. So you will just update your R to this particular index. So what we are doing logically is, we are just taking out the minimum across everything between L and R, and whatever is the minimum, that will be the maximum R possible. Now why minimum? Because we need to stop at first index which doesn't satisfy the given constraints, and whatever is the minimum, if we ignore that, and if we take anything after that, let's say we take everything up till this R, then this part, the one which have the minimum value, will complain, or basically will form a substring that is present in the forbidden list as well. So hope this point is clear. Now what we need to simply do, we can simply update our algorithm by saying that we will now use this min r array. Let's call this a min r array, and we will simply iterate over everything between L and min r and update our r as the min of everything, and rest of the thing is simple. We'll just take the result. So we are still iterating over all the else. Now instead of iterating or finding out the correct r by doing this for loops, like inner loops, we have simply taken the minimum across all the min r's by simply building this array, right? Now the complexity of this is still order n square, but this is better than the previous one which had fl square and log n as well. Now just a side note, you can decrease the iterations here by a simple trick. What you can simply do, you can, instead of iterating over everything up till r, you can simply iterate over the updated r. So this was the initial r, right? So instead of iterating over everything between L and initial r, you can iterate over everything between L and updated r. How that will help? Because r is decremented, you don't need to now take care of anything after r. So let's say if r is here, if you take the value minimum min r value of this one, this will be greater than this r for sure, because L itself is greater, right? So basically what we are doing here is, instead of going all the way to min r, we are simply going up to the updated r. So notice that r is something we keep on updating dynamically. So this will not affect the worst case complexity, but this will surely boost up your average case time complexity. So this is just an optimization in case you need this kind of trick in any other future context. So for now, this is our algorithm, and the complexity of this part is order n square. But there is still one part left, which is building this array. We haven't discussed about that, so let's discuss about that first. So building this array is straightforward. Let's what this array denotes? This denotes the index up till which nothing will match, right? So what you can simply do, you can simply start. Let's say you have to fill the value at this particular index I. You can simply start at this particular index. You can keep on iterating and figuring out if there is a match. So if this is a match, then you will simply update its value to the previous index. If this is not a match, you will try next possible thing and keep on doing that. So basically in this case you will say whether A is present in the list or not. It is not. So let's try AA. Is it present? No. AAC, is it present? No. AACB, no, and so on and so forth. So basically nothing will match, so you will just simply put 9. Basically up till 9 nothing will match. Similarly this will be 9 because of same reason. A will not match, AC will not match, ACB will not match, ACBA will not match, and so on and so forth. For this one instead, C will not match, but CB will match. Because CB is matching, you can't go above B, so you will simply update this to 2, right? And in the same fashion you will fill the other things as well. So the pseudocode for this would look something like this, very straightforward. We will simply iterate over all the I, and for each I we will have to figure out the first index up till which everything will match. So we will keep on incrementing our R until there is a match, and notice that we can simply stop at I plus 10. Why? Because the length of longest string in this forbidden list is 10. So if there is no string which is of greater than 10 length, there is no point that they could match, right? So we can simply stop at 10 and check if it exists. If it exists, we will update the min r to that particular r and break out from the loop. Otherwise we will continue. Now the time complexity of this thing, order n into fl, where fl is the maximum length of the forbidden string length, and then multiplied with this is exist, which will take log of f time. where f is the total number of forbidden string. Now again, this log f is not really log f. I keep on saying this log f is actually fl into log f or something of that order, because you are comparing two strings here, right? Now this will pass the given time constraint because n of words dot length is 10 to the power 5. So this will surely pass the given time constraint. So the overall algorithm that we have now is something like this. We have this part which will compute the value of min-r array, and then we have this part which will actually give us the length of the largest substring. This part works in order n fl log f, which will be sufficient for the given time constraints, but this part will work in order n square in worst case, and this will not be sufficient for the given constraint. So we need to optimize this. Now how to optimize this? Again, two choices again. Either you will skip iterating over all the else, or you will skip iterating over all the r's. That's the only two choice. So both is possible here. I would strongly encourage you to pause and try to think how to do each of them by yourself, right? So hope you have thought about it. Let's start with discussing about how to remove L. So removing L means that we have to somehow figure out that if some L to R is valid, based on that decision we can skip some else and move forward to some other else. For example, let's say in this particular case we have just removed one string from the forbidden list and updated the min-r array accordingly. Now in this particular case this L to R is valid. Now this L to R is valid and L to R plus 1 is not valid because this AAA exists here, right? So basically up till here is valid, this L to R is the first one which become invalid because of this AAA, right? Now until this AAA is there, no matter what you do, your R will stop here itself, right? So basically if you update it to L plus 1, even at L plus 1 this will be the destination, right? Similarly if you update it to L plus 2, this is the destination, because until this A is removed, your R is bound to stop here, right? So with this we can simply say that okay, because this L to R is valid, we can simply update our L to the first index of the matching string, or due to which R stopped here. If we do that, we can simply skip lot of else. Now how many else we can skip? Let's look at it. What is the length of this string? Length of the longest string possible is 10, right? So basically if L to R is x, you will be skipping x minus 10 indexes. So in other words, for every L you are introducing 10 new indexes to iterate upon again. So you have already iterated over this thing with L to R. Now you are saying that you have updated your L to this. So basically you are iterating over this 10 indexes again. So in other words, the complexity would be W into 10 or N into 10, where 10 is the length of the FL. So it can be written as N into FL. So hope this entire thing makes sense. So what we will do, instead of this, we can simply update our L. Instead of iterating over all the L's, we can simply update our L to max of L plus 1 comma R minus 10. Why max? Because if R minus 10 is before L, then you should increment at least once, right? So that's a logic. So with this, the complexity is now reduced to order n into FL from order n square. Now n into FL for this part, n into FL into log f for this part, and this will surely pass the given time constraint. Now let's see how to remove R. Let's say you need to optimize this. Again, I am not showing you the code for this because code would be exactly similar to pseudo code that we have seen here. So we will look at it afterwards. But for now, let's see if we can remove this FL from time complexity as well. From this particular time complexity. From above we can't remove. There is no other point. We will look at it afterwards. But for, let's say, if we can remove FL from the time complexity of this particular thing, the answer is yes, you can remove it very easily. Let's see let's see if we can remove iterating over all the r's. So instead of we will iterate over all the l. Now instead of iterating over all the r, can we get the value without iteration? So what we are doing inside this, we are just simply taking up minimum, right? So what we can simply do, we can simply maintain a segment tree over this array and take the minimum over L to R, and that will give us the value of R in log n time. So the complexity would now then be order n log n. So it is completely independent of the fact how long is the string in the f, right? So next, let's look at one follow up. So we all, like, this was just one follow that we just discussed. Like, we want to reduce the time complexity of this part, and we discussed that we can simply skip iterating over all the r's instead and do a range query over a segment tree that will give us the value. Let's discuss one more follow up. One more follow up could be the complexity of this part is w into fl. So this 10 is fl into log f. Now this is passing because the value of w is 10 to the power 5, but if it is 10 to the power 6, this will not pass. So 10 to the power 6 into 10 into log f will not pass, and we need to optimize it. So that's where we need to think of something else. So this if you remember, this was just the brute force solution that we have come up with, and this was within the time constraint, so we haven't really optimized this. So I would encourage you to pause the video and try to think how to optimize this particular solution. So the answer is try. You can notice what we are doing here. We are simply where from this log f is coming from because of this matching, right? So string matching can be done very easily using try. So what you can simply do, you can simply maintain a try over the list of forbidden strings AAA, BC and CB, and as usual you will maintain the end markers of the try so that you know where the string is ending. Now for each starting point, let's say you have to fill the value for this particular index I, what you will do, you will start from here, you will start from root of the try. Now what you will do, you will check, okay, A is there, so let's just move to A. You reach here, you will go to the next node, you will again see A, let's move forward, you go to next node, you see a C, there is no C at all, right, beneath. So you reached at a non-existent node. So basically it means that nothing is matched at all, because whatever nodes you have visited has value 0 already, so nothing is matched. So this you can simply update it to the largest value. In the same fashion, this will be updated to the largest value. Now let's see what about this. If you have to start with this, again you will start your journey from the root of the try. C, you will go to C. Now you will increment this. B, you will go to B. Now notice that you reached at a node which is a ending position of a particular string in forbidden string. So basically you are saying that this is a matching substring which is present in the forbidden string. So you will simply update the value to one less index. So the value here would be 2, right? In the same fashion you will fill all every other things, and if you do this, the complexity is now reduced. How? First let's see how to build this try. So building this try will take just order fl into f time, right, where fl is the total fl into f, or basically summation of fl into f, right, summation of fli into f. So this will be the overall time complexity to build this try, right? Basically you have to iterate over all the strings just once. Now after you have done this, this part will take you, for each I, what you are doing, you are iterating over the try. What is the max depth in this try? Max depth could be the length of the longest string here. So length of the longest string here is fl, let's say. So the complexity for each index is fl, and how many indexes are there? Total n. So the complexity would be n into fl, right? So we have reduced the complexity from n into fl into log n or log f, which was not actually log f, it is x into log f, to n into fl itself using try. So let's look at the code for this one. Again, I would strongly encourage you to pause and try to code this entire thing by yourself first, because we have done nothing fancy here, just simple try. So let's look at the code. The code is straightforward. What we have done, we have simply built a try class and we have inserted everything to that try, all the forbidden string. Now for each word we have figured out the max, we have to figure out the max r. For that we are calling, like we are first figuring out the substring, uh, because we know that length is 10, so we don't want to grow above. We will simply call the smallest matching substring over the try, which will do this exact same thing of iteration over the try, which we discussed, and we will update the value of max r. After that, once we have max r, we have to simply apply this particular algorithm, or we can simply use segment tree here to make it w into log w as well if you want. In this particular thing, like segment tree doesn't actually help much because FL is already there in this time complexity, so you can't do much. So that's where I haven't called a segment tree thing, but you can try out as well. If you are new to segment tree, there is already a playlist there in which we have discussed segment tree from scratch with the very basic thing to advanced problems as well. So I will link the playlist and you can try that solution as well by yourself. So what we are doing, we are simply iterating over all the i's or all the l's and figuring out the maximum r for each I. And once we figure out that, we will simply update the result and update I to max of I comma r plus r minus 10. Why I minus 10? Because as we have discussed already, the length of the maximum string is 10. So there is no point checking for any other previous string, because whatever r was there for I, same r will be there for I plus 1, I plus 2 until you have get rid of the last string. Now let's look at the try class. Try class has the constructor is simply initializing the node. Node has two things: a boolean which denotes whether a string is ending here or not, and of child pointers. So as you can see, it should have two things: a boolean that contains 0 or 1 and child pointers, right? So that's what it has. So try initializes that. After that, for inserting, we are simply calling insert here, starting from the root. So see what we are doing. We are simply doing a recursion. We start from here. We saw the first letter A, so we inserted A. Now after inserting A, we updated the root node to this and simply call the same function to insert the next position. So that's what we have done. We figure out the current value, we inserted that value, and then we will call the same function again with the next index, right? And if we reach at the end of the string, we will simply update that it is the end of the string. Now finally, the last function, which is smallest matching substring, we are calling smallest matching substring internally with the root node of the try and the 0th index here. As discussed, we will keep on iterating over this one by one and over the try one by one. Either we will reach at a non-existent node, or we will reach at a node which is the ending of a particular string. So that's what we are doing. We are checking if it is a ending. If this node is an ending string, then we'll simply return that length. If it is not an ending string, we'll say if there is more to consider in this string. If not, again minus 1. Otherwise, we will check and go down one level, and if we reached at a node that doesn't exist, then we'll simply return -1. Otherwise, we will call the same function again. So hope this entire solution makes sense. If you have any doubts in any of the solution that we have discussed, feel free to post them in the comment section below. I would be able to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.